Hello and welcome back, everyone. Today we'll be doing section 10.7 on complex numbers. So the idea of growing from one number system to another is not necessarily a new one. Way back in your elementary school days, you started just with what are referred to as the natural numbers. Some people think of them as the counting numbers. So just 1, 2, 3, 4, and those can go as high as you want them to go. So one important number that was missing that eventually they started introducing was the number 0. And if we throw in the 0, then we have the set of whole numbers. So we have 0 and then 1, 2, 3, 4, all the ones that we had before. So in other words, the natural numbers were part of the whole numbers. And then eventually we started learning about the idea of subtraction and the opposite of whole numbers. If we include all of the opposites, we have the set of integers, usually represented with a z, occasionally with an I, usually with a z. So we not only had 0 and 1, but we also had -1. We had 2, we also had -2. And we have those going forever in then both directions. So notice all of our previous number sets are still contained within those. We started working eventually with fractions. We call those the rational numbers, usually represented with a Q. And then that's the first one that I can't use this roster notation. I can't just list out elements. So we would use what's called set builder notation. I write a set of instructions. So a set of all P over Q such that P and Q are in the set of integers, and Q, since fraction bars mean division, Q is something other than 0. The reason I can't just make a list like before, sure, maybe we can put 0 in the middle, but then what's the first fraction we left after the 0? Someone might say 1/2. It's a reasonable place to start. Someone else might say, well, we work in a base 10 number system, so maybe 1/10. Someone else might say, well, we work with money a lot, and that goes out 2 decimal places, so I think 1/100th. And really, there's no right answer as to what would be the next reasonable rational number to list out next. So we just list out the set of instructions. But all of these numbers we listed before, you can all put them over a 1 and make them look like a fraction. 1 is an integer, 1 is not worth 0. So then we threw in the irrational numbers. I'm not going to spend too much time defining the set. That would be numbers like pi or square root of 7, numbers that can't be written as one integer over another integer. The decimal version of these numbers goes on forever without terminating or without repeating. Terminating would be like 1/4 turns into 0.25, hard stop after that, or 1/3, 0.3, and the 3's just keep going forever. And pull all that stuff together, and we have where we've been working for, the set we've been working with most of your math career, then the set of real numbers. So you can kind of see a sort of picture version of that. You have the set of natural numbers, which are contained within the set of whole numbers, which are contained within the set of integers, which are contained within the set of rational numbers. And then we have our set of irrational numbers. Often that's represented with a t. Pool all that together and we have your set of real numbers. So today we'll be working with the complex numbers, which is basically just saying, okay, we're going to work out one more step beyond what we've been working with. So complex numbers answer the question, what happens if I want to take the square root of a negative number? Up until this point in the course, we've just said not a real number. This one we start with a definition. Define lowercase I to represent the square root of -1. With that tool in hand, now we can represent numbers like square root of -25. Until now, all we've said is not a real number. But I can just break that into pieces. Square root of 25 by square root of -1 turns into 5 times I. So all of our complex numbers can be written in the form a plus bi. So a and b are real numbers. I is as defined, square root of -1. So notice all of these numbers we worked with before still follow that pattern. Here is just a is whatever number we were looking at before, and b is 0. 0 times anything is always 0. So sometimes they give us something that we can do a little bit more simplifying with, like maybe square root of -50. I can pull the perfect square, the square root of -1, and then the leftovers. So still following the patterns we worked with before when we were simplifying radical expressions. So this would be 5i root 2. Occasionally you'll see it written in the other order with the I at the end of the line. The reason I tend to avoid that is it's harder to tell then at a glance, did you mean for the I to be under that square root or not under that square root? So I want it to be clear that the I is not under the square root, so I tend to put the I in front of the radical term. So they may give us something like square root of -80. Take a moment, try that one out, pause the video, and then we'll finish it together. Okay, welcome back. So biggest perfect square we can pull from 80 is the 16. So you might have spotted the 4, but you always want to take the biggest perfect square or perfect cube or whatever type of radical you're working with. So square root of -80 is 4i root 5. If you did pull the 4 first instead, no problem, you just have one more step in your problem. So 2i root 20, but 20 has a perfect square factor still. So I just hang on to the 2i, turn root 20 into root 4 root 5, and go from there. So 2i by 2 root 5 turns into 4i root 5. So again, it's much faster if you pull the biggest perfect square factor first. Now, one little heads up as far as breaking these apart. This property works when we're working with a single I and real numbers only. The nth root of a, nth root of b, in general being nth root of ab, works for each of those in the set of reals. So in other words, nth root of a is a real number, nth root of b also has to be in the set of reals. So for example, square root of -1 times square root of -1 is I times I, or I squared. And I squared is worth -1. And we can kind of reason our way through this. Square root is asking what can you square to reach what's underneath here. So I is the number that you can square to reach -1. Therefore, I squared must be a -1. So some basic operations on these things. Multiplying and dividing the complex numbers, we just go to I notation. So for example, root -2 by root -7, we have to go to I notation before we do anything else. So I root 2 times I root 7. I times I is I squared. Root 2 times root 7. Now these are both real numbers. Then I can use that property. So that's the square root of 14. So this is -1 square root of 14. And you'll see it written with or without the 1. You may see it just written as -√14. Maybe has to multiply root 27 by square root of -3. Again, take a moment to switch over to I notation. So we have square root of 27 times I times root 3. So that is square root of 81 times I. So that is 9 times I. And we'll do just one quick division in monomial form. Although these aren't really polynomials, these are sort of the cousin to the monomials. So square root of -1, square root of 8 over square root of 2. So this is I square root of 8 over 2. So I root 4, which is then 2I. So next we look at adding and subtracting when we're written in the A plus BI format. If we pretend that I is a variable, it's not, but we're just going to pretend like it is. Treat it as if it were a variable. Treat I like it's an X. The properties you have are pretty straightforward then. So if we have 5 plus 2I, one complex number, and we add 4 minus 3I, just like you would do if this were a 5 plus 2x and a 4 minus 3x, you would put the constants together, so 5 plus 4, and put the x's together, 2 minus 3 of the i's. So 9 minus I would be our sum. And you can see that that would hold in general for any A plus BI plus C plus DI. First, take down the parentheses. Commutative property of addition next. Associative property also lets us regroup, and distributive property lets us factor the I. The only heads up, just kind of watch for your signs when you're doing subtraction. So 7 minus 3I minus 6 minus 11I. Take one moment to knock down the parentheses using the distributive property. So 7 minus 3I minus 6, watch your signs there, plus 11I. After that, real number component plus real number component, imaginary term plus imaginary term. And then that's as far as we can go. Notice also the order, it's always a plus bi. The I term is always written second in your answer in these. Now, as far as multiplying complex numbers, one thing to remember is that I squared is worth -1. If you remember that, you're all set. So if I have -5i multiplied by 3i, -5 times +3, -15, I times I is I squared. Remember, I squared is -1, so we have -15 times -1, so this would be a +15. So your answer doesn't always necessarily end in something that has an I attached. May have something like -2i multiplied by 7 plus 3i. Again, just think of these as if the i's were x's. You would use the distributive property in this problem. That's exactly how you would approach the complex numbers. So -2 by 7i, -2 by 7 is -14, and we hang on to our I. -2i by +3i, -6 times I squared. Remember that I squared is -1, so we have -14i minus 6 times -1. Minus 6 times -1 turns into a +6, so 6 minus 14i. A plus b times I. I is always the last one written. Okay, so the next one that we're going to play with, we have two terms in the complex constant. We'll do 7 minus 4i times another two terms in the complex constant, and 8 minus 5i. If you saw a 7 minus 4x times an 8 minus 5x, hopefully you would think to FOIL that out. Distributive property basically twice over. That's exactly how you would do this with the complex numbers. You would FOIL it. First times your first. 7 by 8, 56. Outside times outside. 7 times -5i, -35i. Inside times inside. -4i times +8, -32 times I. And L, the last times last. Negative times a negative is a positive. 4 by 5, 20. I times I is I squared. We hit our terms in the middle there, so hang on to the 56 for a minute. Then we have minus 67i and plus 20i squared. Be careful here, we're not done yet. Remember, I squared is a -1. So this is really 56 minus 67i plus 20 times -1, or simply minus 20. So 56 minus 20 minus 67i, and hit your like terms there. So 36 minus 67i would be our final answer on that. And the same thing holds if we have three complex numbers multiplied together. Just take them two at a time. So if we have 1 minus 3i by 2 plus I by, let's do 4 plus I. I'll just multiply the first two, bring the 4 plus I along. So 1 times 2 is 2. 1 times I plus 1i. -3i times +2, -6i. -3i times +1i, -3 times I squared. And don't forget to bring along your 4 plus I. So we have 2 minus 5i minus 3 times, remember I squared is really -1, so we have -3 times -1 is +3 times 4 plus I. And then rather than do all of that extra distributing, finish simplifying that first 3. The 2 plus 3 turn that into 5. So we have 5 minus 5i times 4 plus I. And then we have another small 2 terms times 2 terms problem. So 20, first times first, outside times outside, plus 5i, inside times inside, minus 20i, last times last, minus 5i squared. So we have 20 minus 15i, minus 5 times, remember I squared is really -1, so plus 5. So 25 minus 15i. All right, so I'm going to give you 2 of these to try out, and they're going to lead us into how to approach dividing with complex numbers. So you're going to try out 2 of them. The first one you're going to try is 1 minus 2i quantity squared. The second one you're going to try out is 6 plus 5i by 6 minus 5i. So go ahead and pause the video, try those 2 out, and we'll finish them together. Okay, welcome back. The first one, hopefully you recognized if you have 2 terms and you're squaring it that you're going to need to FOIL, so write it out twice. You won't get the same answer if you just attach the square to each one of these. Remember our counter example, if you have trouble with that, try out 2 plus 3 quantity squared, 5 squared, 25, versus 2 squared plus 3 squared, 4 plus 9, 13, definitely not equal. If you have 2 terms and square them, you can't just square the individual terms. All right, so FOILing out, first times first is a 1, outside times outside, minus 2i, inside times inside, minus 2i again, and last times last, plus 4 times I squared. So we have 1 minus 4i. 4 times -1 is really a -4. So 1 minus 4 is a -3. So -3 minus 4i. Our second one, we just had to FOIL it out. It was already written as 2 terms times 2 terms. So we have 36 minus 30i plus 30i minus 25 times I squared, which gives us 36. Notice here the minus 30i plus 30i is 0. And then we have our minus 25 times I squared is -1, so that's really a plus 25. So that would be a 61. So notice on here, again, sometimes we run into a case where we don't have any more i's left. I remember I is representing a square root, specifically the square root of -1. So this second one is really taking us into what to do with division. They're going to say divide, but we're really going to think rationalize the denominator. So good news for you if you needed a little bit more practice rationalizing denominators. That's exactly how we approach these problems. So if they'll say divide on, we'll do, I don't know, 3 plus I over 2 minus 3i. They'll say divide, even though they really mean, but won't write, rationalize the denominator. This denominator had 2 different terms in it, so we'll multiply by 1 using its conjugate. So 2 plus 3i. And so that I'm changing the look but not the value, I also then have to multiply the top by 2 plus 3i. After that, we have just a couple other multiplication problems again. And 2 terms times 2 terms, we're FOILing it out again. If it helps you to see the parentheses, go ahead and put them on there. So up top, first times the first is 6. Outside times outside, plus 9i. Inside times inside, plus 2i. And last times last, plus 3i squared. Hang on to your denominator. So we're going to keep the whole problem together. We're not exploding out from the middle, going across and keeping the problem together. First times the first is a 4. Outside times outside, 2 by 3i is positive 6i. Inside times inside, there's our minus 6i. There's that cancellation we were hoping to see. And last times last, minus 9 times I squared. So up top we have a 6, we have a plus 11i, and we have, careful here, a minus 3. I squared, remember, is a negative 1. At the bottom we have a 4. Outside and inside cancel out, and we have a plus 9. So we have 3 13ths plus 11 13ths times I, and there's that A plus BI format. Now sometimes we're dividing by something that just has one term in the complex constant. So we have 5 minus 7i, and we are dividing by 3i. On that one, we will just multiply top and bottom by I. That's the only thing that's underneath a square root, and I have one term, not two terms. So a little bit of distributive property up top. So 5i minus 7i squared. Down on the bottom, 3i squared. Our I squares, we remember, are negative 1, so we have 5i plus 7. So minus 7 times negative 1 turns into a plus 7. 3 times I squared is really 3 times negative 1, or negative 3. And then I just change up the order so that we have the real number plus b times the I number. So negative 7/3 minus 5/3 of I. All right, so let me put one up for you all to try, and then we'll get into powers of I, since we can obviously go higher than just a second power. So I'll have you all try 4 plus 2i divided by, what did I pick last time? 3 minus 5i. All right, so pause the video, give that one a try, and unpause when you're done. Okay, welcome back. So our conjugate of 3 minus 5i is 3 plus 5i. So we'll multiply top and bottom by 3 plus 5i. So just a pair of foiling problems then. So up top, first times first is 12. Outside by outside plus 20i. Inside by inside plus 6i. And last times last plus 10 times I squared. Down at the bottom, first times the first is 9. Outside by outside plus 15i. Let's see, outside by outside plus 15i. Inside by inside minus 15i, and last by last minus 25 times I squared. And then just remember, I squared is always worth a negative 1. So now we have 12 plus 26i minus 10 over 9 plus 25. So the 15i minus 15i is 0, minus 25 times negative 1 is plus 25. So upstairs, 12 minus 10 is 2. Downstairs, 25 and 9, 34. And then plus 26/34 times I. And then we just do a little bit of reducing. So that would be 1/17 plus 13/17 I. All right. So then the last thing we'll look at are the powers of I. So we know that square root of negative 1 is just an I. We do know that negative 1 is the same as I squared. So next we use those two to find I cubed. I cubed is I squared times I. I squared, though, is a negative 1. Negative 1 times I is the opposite of I. I to the fourth is I squared times I squared, which is negative 1 times negative 1, which is a positive 1. And after that, they're just going to keep looping around. I to the fifth is I to the fourth times I, 1 times I, which is just back to an I. I to the sixth is I to the fourth by I squared, which is 1 times -1, which is the -1 again. I to the seventh, I to the fourth times I cubed, 1 times I cubed we found to be -I. I to the eighth, I to the fourth, squared, which is 1 squared, which is 1. And really, this I to the fourth is the key, no matter how high you want to go. Let's see how far we are into the video. Let's see, 30 minutes, 46 seconds. So if I do I to the 46th power, I'm going to try to take advantage of the I to the fourth. I'm going to get as many I to the fourths out of this thing as I can. So I to the fourth to the 11th, power to a power, remember we multiply them. There's 44 copies of the I spoken for. So I only have 2 more to go. So there's all 46 copies. I to the fourth is a 1. 1 to any power is a 1. And I squared is -1. So I to the 46th is a -1. Let's see, now I'm 29 seconds in. So I to the 29th. I to the 4th to the 7th. I to the 28th, so that's the closest I can get without going over. Got 28 copies spoken for already. I need 29 altogether, so just 1 more. So this is 1 to some power times I. 1 to any power is always 1. 1 times I is just I. So let's see. So I'll have you all try I to the 32nd and I to the, 49th. So pause it, give those a try, and we'll do them together. Okay, welcome back. So I to the 32nd, I to the 4th to the 8th, and nothing left over. That landed us on exactly I to the 32nd, so that's 1 to the 8th, which is just a 1. I to the 49th, so I to the 4th to the 12th, so there's 48 copies spoken for. I need 1 more. So that's 1 times I, which is just I. Okay, so that does it for Chapter 10. Problems to try out from 10.7, 1 through 85, every other odd. So if you have questions, please feel free to email me. Otherwise, stay safe out there, and I will see you next time.